Next topic is inductor. The solenoid is nothing but inductor. So it's nothing but a coil. Take a wire, make it as a coil, that will act like a inductor. Okay, solenoid is nothing but inductor. So we know that from the previous chapter. Okay, there is always a constant amount of magnetic at any point there is always a constant amount of magnetic field at any point. The value of that magnetic field B equal to mu naught n I over L. B is magnetic field. Okay, B is magnetic field. L is length of the solenoid, and n is nothing but number of turns, and I is the current. So this is the magnetic field produced by a solenoid or inductor. This inductor we indicate with the L, okay, measured in Henry. Okay, so basically if you say an inductor, you say 2 Henry, 2 millihenry, or 5 millihenry, 5 microhenry, something like that. Okay. Now there are two important properties of this inductor. The first one is it stores energy. That energy is half Li square. It is almost similar to the capacitor. Let me put capacitor here. Okay, here is capacitor C measured in farad. This one stores energy, capacitor stores energy, which is half CV square. Same way, inductor stores energy, that value is half Li square. By the way, capacitor stores in the form of electric field. Okay, inductor stores energy in the form of magnetic field. It stores energy in the form of magnetic field. Okay, now another important property, so this is really important one. Another important property is inductor, it opposes rate of change of current. Okay, so it does not allow sudden change in current. That's inductor. That's another important property. If you remember capacitor, it opposes rate of change of voltage. That's with the capacitor. So I'm just comparing inductor and capacitor. Now to find out this L value, L equal to d phi by di, or you can say phi b, where magnetic field, over I. If you remember, C is nothing but Q over V. So capacitance always related to voltage, inductor always related to the current. Okay, here inductor is always magnetic field, capacitor is always electric field. Okay, now L equal to phi b over I. Now I know what is the magnetic field inside that inductor. Can I find phi b is BA, where A is cross-sectional area of the inductor. Okay, so when you look at on the side, okay, this is what we see from the side view. So this cross-sectional area is nothing but pi r square or pi d square by 4. Okay, BA. Now phi b, I can say mu naught n I over L times A. Now if I substitute in this one, okay, now by the way, here this is for one turn, you can say I would say this is n times d phi by di. N is number of turns. I would keep the n there too. Now L value is n times d phi by di. N is number of turns everywhere. So if I substitute this one in this equation, I get cancelled out. Mu naught n square a over L. This is nothing but L. So what I'm doing, I'm substituting this value right there. So this is the inductance value. Inductance is nothing but mu naught n square a over L. L is length of the solenoid or length of the inductor. If you remember, capacitor also has the similar formula, C equal to epsilon naught A over D, and there is a constant. This constant is dielectric material constant. Okay, so electric field always related to this epsilon naught, another constant. Magnetic field always related to the mu naught. Now voltage across inductor. Voltage across inductor. So according to Faraday's law, there is always an induced EMF E equal to minus n times d phi by dt. As long as there is rate of change of magnetic field, there is always an induced EMF. Now what happens? So here is an inductor. What happens if this magnetic field is constant? So if B is constant, where do you get constant magnetic field? As long as, I mean, if it is DC source, whatever the power supply is DC source, we say B is constant. Okay, constant magnetic field. If B is constant, what is the induced EMF? E equal to 0 volt. When we're going to have 0 volt, that's a short circuit. So basically, if I connect this to a DC source, that will produce a constant magnetic field. Whenever I see constant magnetic field, the voltage across the inductor is 0. So in DC, inductor acts like a short circuit. Okay, when you compare this with the capacitor, do you remember in DC capacitor act like a in DC capacitor acts like a open circuit. Okay, in DC capacitor act like open circuit. I think I'm going to make another video comparing those capacitor and inductor later on. Okay, now if this is AC source, assuming that instead of DC here, say I connected to the AC source, that means it's alternating magnetic field. This coil is going to have alternating magnetic field, so phi is keep changing. Okay, the phi is going to keep changing. Now can I write this E equal to minus n times d phi by di minus n times d phi by di and di by dt. Okay, can I write that? I just extended this minus n times, and instead of d phi by dt, I'm convert this into d phi by di and di by dt. Now we already know that n times d phi by di is nothing but L. So the induced EMF across the inductor is nothing but L times di by dt. Okay, now what happened to this negative? We can indicate that negative. Basically, the induced EMF always oppose the rate of change of current, L times di by dt. That's the voltage drop across the inductor. Okay, to avoid confusion, I'm going to keep this minus there, so it's not good. So what happened to this minus? This minus already I So assuming current is passing in this direction, so this negative indicates that that is opposing the flow of current direction, so that negative is already indicated here in the sign. Now we'll find energy stored in the inductor. Okay, what is the energy stored in the inductor? I know the current, I know the voltage, so can I say power P equal to V times I? So that's nothing but E times I. E is L times di by dt times I. Okay, I'm going to choose this as direct current. So if it is direct current, there is no voltage drop across this, but still it holds some energy, so we'll find that energy. Power or energy is nothing but power times time. Okay, or power is nothing but, can I write this as du by dt? Okay, so I'm going to say power equal to du by dt, which equal to L times I times di by dt. Now if I integrate on both sides, I will end up with U, which is energy equal to U times L times integral of 0 to I times di. Okay, so once you're done with the integration, energy stored in the inductor U of L equal to half L I square. This is the energy stored in the inductor. Thank you.